Hello and welcome back. So now that we've expanded our set of models to include models that can experience uncertainty, it's time for us to now think about how you might compute them. Computing these equilibria is important in macroeconomics and in other fields as well because it allows us to use a dynamic model to answer quantitative questions where the answer is a number. For example, to what extent do productivity shocks account for fluctuations in output? In order to do that, we need to figure out how to compute these models, and that's what we're going to do now. Let's take a look. Let's start by writing down the preferences and technology. So we have a bunch of households, and they maximize expected discounted utility. The word expected is important because, of course, there is uncertainty in this environment. E sub 0 means the expectation at date 0, although, of course, they're going to be able to update their beliefs every period as new information is revealed. Here is the sum over periods t from 0 to infinity. Here is the discount factor, rho. And the utility function will have two arguments. One will be consumption, and the other will be leisure. The households have the following constraints. One of them is that agents are given a certain endowment of time. Let's normalize it to equal 1. And leisure must be taken out of that endowment. Second, agents may also work. And the time that they work must be less than or equal to their time endowment minus however much time they spend on leisure. Of course, we can collapse this very easily if we assume that utility is strictly increasing in consumption and leisure into a much simpler form where we just remove these constraints altogether and write utility in terms of 1 minus the time spent working. Next, there is a production function, f, which produces output, which may be used for consumption or investment, and a capital accumulation function. However, again, for brevity, let's just collapse the two into each other and say that capital tomorrow and consumption may not exceed whatever capital there is left over from last period plus output. And output is coming from a production function f, which depends on capital, on labor, and on a productivity term z. So this collapses together the resource constraints and the capital accumulation function. There is also going to be a law of motion for z. Let's just say that z follows an AR1 process with a random disturbance. The random disturbance will follow some stochastic process. Typically, it's going to be drawn from a normal distribution with mean 0 and variance sigma squared. Another constraint is that, as usual, the initial capital is given. To go further, we're going to want specific functional forms for this utility function and this production function. And we are going to proceed with the following. Utility, as a function of consumption and leisure, is going to be the following. First, we're going to have the standard CRRA utility form for consumption. I already use sigma here, so why don't we use a subscript epsilon to make sure that we're distinguishing between this sigma and this one. Next, we have to figure out what to do about leisure. And we're going to treat leisure in the same way. So there'll be another CRRA function here. And finally, we'll want to add a parameter that's going to govern how much agents care about leisure relative to consumption. So let's just add a weight theta here. So that's our utility function. As theta goes up, agents care more about leisure. As theta goes down, leisure becomes less important compared to consumption. Next, the production function. We're going to set a production function equals to e to the z plus the typical Cobb-Douglas form, so k to the alpha and n to the 1 minus alpha. So that's it. We now have everything we need to proceed. The next thing we need to do is to write down our necessary conditions for an optimum. The first is going to be the Euler equation, which we obtain by differentiating with respect to capital tomorrow, and then by taking the envelope condition, if it's the recursive problem that we're solving. And that's going to look like this. The discounted expected marginal utility from consumption tomorrow times the expected marginal product of capital tomorrow should equal the marginal utility of consumption today. So when you sacrifice 1 unit of consumption today, what you lose on the margin equals what you gain in expected terms tomorrow. Feel free to pause here while you work this out by yourself. The next necessary condition is the first order condition of the planner's problem with respect to labor. And this is going to give us something very useful. First, let's work it out. Again, pause if you want to work it out for yourself. This is the marginal utility of leisure, or the marginal disutility of working. That should equal the marginal utility of consumption times the marginal product of labor. And notice that this condition contains no terms at dates other than t. In other words, we could rearrange this equation so that we have c as a function of capital, labor, and the productivity term z, where that function is given implicitly by this. Very easy, just divide both sides by all of that, multiply everything to the power of 1 over minus sigma, and we'll have that function. So this means that we can reduce our system by 1 variable by simply replacing CT everywhere with this. So this would show up here, and this would show up here as well, but with t plus 1 indices instead of t. So what this means is that now we have solution to our problem as the solution to a dynamical system with 3 equations and 3 unknowns. One of these 3 equations is this Euler equation, which tells us how CT goes to CT plus 1. And of course, it also depends on these other things. Now we've eliminated C as a variable, so we would replace this with this. And replace C here with that. Again, being careful to get the indices right. So now you can see what I meant when I said that we have 3 equations and 3 unknowns. Here's the first equation, and these are our 3 unknowns that change over time. The second equation is just this. We set it to equality because we know that utility is strictly increasing consumption and leisure. And again, we replace consumption with this. So again, we still have only 3 variables changing over time. And finally, the last dynamic equation that describes our solution is this, the law of motion for productivity. To proceed further, it's useful to do the following, which is going to help us summarize this in matrix or vector notation. Let's define a variable xt as this 3×1 vector of k, n, and z. Next, let's take these 3 equations and instead write them in the following form. Let me first of all put them all in the same box. What that's going to do is line up all the equals signs. And you can see that on the right here, if I subtract consumption from both sides in this middle equation, we have only terms that depend on xt. That's these 3 variables summarized in a vector, as opposed to t plus 1. And on the left of the equal signs, we have 3 equations that depend only on t plus 1 realizations and don't depend on t. So we could write this in the following way. You could stack these 3 expressions, 1, 2, 3, and just call them a vector-valued function g. The expected value of a vector-valued function g, which is nothing more than these 3 expressions stacked. Of course, g is a function of xt plus 1. Similarly, we can stack these 3 things, leaving out the epsilon. Finally, we want the random component here, vt plus 1, which is simply the following. Vt is the random component of the first, second, and third elements of this vector of functions. The random element of the top one is 0. The random element of the second one is 0. The random element of the third one is epsilon. Great. So the solution to the planner's problem is the solution to this dynamical system. There's one more condition that I haven't written down, which is the transversality condition. Keep that in mind because it's going to be important later on. The next thing we need to do is to remember that if there were no uncertainty here, then this model is going to converge to a steady state. A steady state being a value of k and z such that xt equals those values for all t. And what we're going to do is assume that since uncertainty is essential to a model, we have to assume that this is going to be positive. However, the key assumption is going to be that we never stray too far away from this steady state. And how is that useful? It's useful because it means that we can take Taylor approximations around the deterministic steady state here and use those approximations to help us better understand this dynamical system and eventually as tools for simulating it. If you look at this, we know that z star is going to equal 0, assuming that mu is inside the unit circle. And the values of k star and n star can be readily found by using these equations and just erasing the time subscripts. You could use fsolve or f0 in MATLAB to do that, but the calculations are fairly straightforward. You could probably do them by hand or in Excel. So more broadly, how is it that this deterministic steady state is determined? It's determined by the condition that when we remove uncertainty here, x does not change over time. In other words, the deterministic steady state is given by the condition that g of x star equals f of x star. So we'll use that in a second. More broadly, it's going to be true that the expected value of g here is equal to the expected value of g evaluated at x star plus d of g. What's d of g? That is the matrix of derivatives of the vector function g evaluated at x star. Why are these derivatives a matrix? It's because g is a function of 3 things and g has 3 rows. So you have to derive each row by each of the arguments, and that way you get 9 derivatives. We're going to organize them into a matrix, and that's d of g. Evaluate that at x star and multiply it by xt plus 1 minus x star plus some small o of xt plus 1 minus x star. And again, because we're writing expected value here, we have to put that there as well. Although, observe that there is no uncertainty here about g of x star. Those are just numbers. And there's no uncertainty about d of g either, evaluated at x star. Those are also just numbers. The only uncertainty here actually has to do with this. And I guess here we can put the expectation inside the small o. The same is true of f, except that f is known, and it's a function of t not t plus 1, that equals f evaluated at the steady state plus the matrix of derivatives of f times the deviation from x star plus some small o of the deviation of xt from x star. Plus, of course, the random vt plus 1. Next, remember, these two are actually equal. So let's put them together here and set them equal to each other. We can simplify things here quite a bit. How come? Well, we know that g of x star equals f of x star. So I can replace this with g of x star. And of course, if I subtract g of x star from both sides, I end up with this. Finally, if we assume that these things are small, then what we have is an approximation to our system that is linear. This is a matrix. This is a vector. This is a matrix. This is a vector. And this is a vector of random variables. So what we're going to do going forward is the following. We're going to set this to be an equality. And we're going to do the following. We're going to introduce a new random variable w, which equals v, so this vector 0, 0, epsilon, plus any uncertainty here that's associated with the value of xt plus 1. In other words, we're going to remove this expectation here and say that any uncertainty here is just soaked up by this random variable w. Finally, we're going to introduce some notation to make this more compact. We're going to define a matrix psi, which is equal to this, the matrix of derivatives from g evaluated at x star. We're going to define a matrix big phi, which is equal to the matrix of derivatives from f evaluated at x star. We're going to define a new variable x hat, which is equal to this difference between xt and x star. And that's going to allow us to write this whole thing in a more compact form. This is psi. This is x hat evaluated at t plus 1. This is x hat. And this is big phi. Excellent. To proceed further, you will need to remember some of your linear algebra. And if you're not sure about this, you can look it up. So let J equals the inverse of psi times phi. Next, let Q be the matrix of eigenvectors of J. Let capital lambda be the diagonal matrix of eigenvalues of J. Then it must be that this diagonal matrix of eigenvalues lambda is equal to the inverse of Q, the matrix of eigenvectors, times J times Q. This is a theorem. And now we're going to use that to manipulate this difference equation in a way that's going to help us solve our model completely, at least in an approximation close to X star. First, pre-multiply both sides of this equation by the inverse of psi. Let's do that there, here, and here. And now let's pre-multiply everything here by the inverse of Q. Great. What happens next? Well, these two matrices are inverses, and so they equal the identity matrix. Notice that here I could insert the identity matrix and it would change nothing at all. That means that if I insert an expression that equals the identity matrix again, I will change nothing at all. So let me do that. So I'm going to introduce Q times Q to the minus 1, which of course equals the identity matrix. How does that help me? Helps me quite a bit, because this is J. Moreover, from what we saw before, this equals lambda, the diagonal matrix of eigenvalues. How does this help us? It helps us quite a lot, because now we have a new difference equation, not in terms of x hat, in terms of Q to the minus 1 times x hat. And because lambda here is a diagonal matrix, it means that if we unstack this vector valued equation and write it in terms of this variable, the first equation of the unstacked expression will have the top element of this and will not contain the second or third. The same will be true of the second element, and the same will be true of the third one. So let's redefine a new variable s sub t, which is equal to Q to the minus 1 times x hat. We can rewrite this in terms of s. So this becomes s. This becomes s. And here we just have some function of our random variable. And again, because lambda is a diagonal matrix, that means that when we write this out, we'll get the following. Let's make this a vector, and let's say the top element is st plus 1 with a superscript 1. This is the same with the superscript 2, and this is the same with the superscript 3. This is st, and lambda is the following. And again, this is just some random variable. We could give it a new name. We could call this whole thing let's say, omega. Now everything looks neater. What we can see, as I was saying, is that we can unstack these as independent equations. S1 t plus 1 equals lambda 1 times this, times 0 plus this, times 0 plus this. So it just comes out to be st plus 1 subscript 1 equals lambda 1 times this plus the first element of omega, whatever it is. The same is true of the second element here and the third element here. How does this help us? It helps us a lot, because if you compute this, and in particular when you compute lambda here, you will find out that there is one and only one eigenvalue that is outside the unit circle. This actually follows from the fact that this growth model has, that the equilibrium in this growth model has the saddle path property, meaning there's one and only one path whereby you approach the steady state. This can be proven easily in the continuous time version of this model, which we'll do later on when we talk about the Ramsey-Cass-Koopmans model. But if I'm not mistaken, this model is topologically equivalent to that one, and so it also has the saddle path property. So suppose that lambda 1 is inside the unit circle, then any disturbance here is going to affect st plus 1, but then its influence in the following period is going to be mitigated because lambda 1 is inside the unit circle. So the influence this has on future periods is going to be diminished gradually over time by lambda. On the other hand, if lambda 1 is outside the unit circle, that's not going to be true. And the influence of any shock today that changes this, when we get to tomorrow, that influence is going to be magnified by being multiplied by some number that's bigger than 1. And so, of course, that means if we suppose that lambda 1 is the eigenvalue that's outside the unit circle, that S sub t is going to explode. And of course, that's not consistent with equilibrium. It's not consistent with the transversality condition intuitively. The only way to avoid this system exploding is if this is always obliged to equal 0. And this is called a linear restriction, and it's the hallmark of these models, and it's the hallmark of the procedure used to solve and compute them. How does this help us? Well, remember, S is a function of capital, labor, and productivity, or rather it's a function of their deviations from the steady state. What function? Well, if this is S1 that we're talking about, it's just the first row of the inverse of Q. So st sub 1 is just some function, some linear function of k hat n hat and z hat, where we get these coefficients again from the first row of inverse Q. And what we've just seen is that this has to equal 0 at all dates. And if we rearrange it, we'll see that we've solved our model. Why? When you wake up in the morning, you observe the value of productivity that you have to deal with because epsilon is drawn from its distribution. You know what capital is because it was determined in the previous period. It's the choice of labor that we don't have in order to solve our dynamical system. But this equation tells us what labor must be. It must be this. And that's it. So take this condition, going back to our system here. We know what Z is, we know what K is, and that condition gives us N. So that means we know the value of everything on the right-hand side here. For next period, we draw an epsilon t plus 1. It gives us this. This equation pins down that. So next period, we know what kt plus 1 and zt plus 1 will be. We wake up the next period, and again, we know what nt plus 1 has to be because it has to satisfy this condition. And that's how we can simulate this model with aggregate uncertainty. We have to start with k0, but we just make a series of draws of epsilon, which allows us to create a sequence for zt. And then we just use this equation to figure out what nt must be in each period. And that way we can generate series for any of the macroeconomic variables that characterize our model economy. One question you might wonder is, well, what k0 should we start with? And you should be starting with a typical number, whatever that means in this context. And so what's usually done is that you start from the deterministic steady state, which of course is not typical, it's a very specific one. Simulate it for, let's say, 1,100 periods, and then throw away the first 100 periods so that your choice of initial condition doesn't end up really having much influence on the behavior of your model. And that's it. This is what we need to do. Great. So the next question is, how are we actually going to simulate this? You could program this dynamical system in any programming language or programming environment of your choice. I use MATLAB. There are other options such as R and Mathematica. But a group of economists got together and decided, wouldn't it be great if, just the same way that you have programs like Stata and SAS to do econometrics for you, so you don't have to program everything every time, what if there were a similar utility that you could use to simulate business cycle models? And they wrote something called Dynare. So the best thing to do in order to simulate these models is just to use Dynare, where all you need to do is enter the 3 dynamic equations for this economy, the Euler equation, the capital accumulation equation, and the law of motion for the productivity shocks. You have to enter them in the right way, and then you can simulate a business cycle model fairly easily. It's a wonderful tool, and it's the best way to do it. However, in the same way that you should not use Stata or SAS, for example, to do any econometric work unless you've already studied econometrics, because otherwise you don't know if what you're doing makes sense. Similarly, it's important to have gone through the class that we went through today so you understand the mathematics of exactly how is it that Dynare is working.